So kind of related to that discussion are now site-related dependencies. So that was site and atmosphere. That's where the adjacency effect comes in. This is really two sites, different sizes, different kind of characteristics, what might be the differences between them. We had multiple data sets for each, a total of almost 60 data sets for both of them. Different sizes, different aerosol types, surface heterogeneity, surface reflectances. Are there things that are going on there that we don't know about? And again, just to reiterate, final answer, we see no statistically significant difference for Landsat. I showed this a bit ago, but we do see it for ASTRO. And it's a noticeable difference, especially out here at band 9. And what we really noticed was at White Sands, it was tremendously different. If I did the White Sands plot, the White Sands would be somewhere up here, almost a factor of 2 or 3 different. And the life of, this is what you'll have to get used to. If you do reflectance-based calibration, you do vicarious calibration, you go to the first science team meeting and you present results like this, and they just basically go, what's wrong with your method? You go, well, no, I have these results here, and nothing's wrong with my method. I think there's something wrong with the instrument. No, the instrument's fine. No problem. You know, you guys, you have an atmosphere in the way. That was what was the answer? You have an atmosphere in the way. We can't trust your vicarious. About a month after we showed these results at one of the Astro Science team meetings, and all of a sudden there was this big announcement of there's this major problem with the optics. Somebody was looking at an island out in the ocean, and there were like 7 islands where there should have been 1. And it was just light bouncing all over the place. And it was within the focal plane of the shortwave infrared, the wiring was reflecting energy from one detector package up and around underneath the filters to the other detector package. So it's a really difficult thing, an unpredictable type thing. The pre-launch characterization measurements were done in a way that we would not have seen it, we did not see it. And so it was just sort of a big surprise. We knew something was going on, but nobody would trust the vicarious of itself. So what was happening was energy from band 4 was bouncing off of the detectors, because all detectors are only about 30% absorbing. So they'll reflect 70% of their energy. And then it was going up and bouncing around all over the place. And band 9 is the next closest band to band 4. So it was getting a lot of energy. Both because the solar output is larger in band 4 than it is in all the others. The sun is peaking and it's falling off as you go to longer wavelength. So band 4 you have a lot more solar energy. The detector in band 9 is the same detector material, so it gets the same response. It'll collect those band 4 photons just as nicely as band 4 will. The problem is that there's less band 9 photons to work with, because band 9's at a longer wavelength. So now you're adding a lot of photons to something that does not have that many. The other problem with band 9 is that there's atmospheric water vapor absorption in that band. So now you have another reason that you have more photons in band 4 than you do in band 9. And I mentioned that White Sands sort of really horrible situation. If you go back in the charts, and you have this yourself when you do this, remember the problem with White Sands was the reflectance instead of it being fairly flat in shortwave. Band 9 has a really low reflectance. So you have a low reflectance of a low solar output being swamped by photons coming from a high solar output and a higher reflectance. And so we were getting a crosstalk effect that affected the calibration. And at Railroad Valley, it's bigger also, and so you now have a bigger effect because of the fact that you're getting all this mixing of the different surfaces.
Did they fix that, or was it too late?
Fix it? No. Correct for it? Yes. So there's a correction. The drawback of the correction is instead of you getting to use the full scene, you have to know where the energy might be coming from. So you lose edges of the scene to get a proper correction. But they figured out, it's one of those things that you feel badly that we had the problem, but it really was an amazing solution in terms of how they figured out exactly what was causing it by looking at the lunar data, looking at island data, looking at the results as a function of wavelength, as a function of band, and determining exactly where in the design most of the scattering was coming from, which then allowed them to create a theoretical correction as opposed to just being an empirical one. So, phenomenal response to a really bad problem. And it's why it helps to have good pre-launch characterization. We likely would not have fixed it because it would have been found so late in the project. But it would have been nice to have had the pre-launch data collected in a way that it would have found that issue, so that it was not such a surprise. But this is entirely because of the different sizes. And the reason is that Ivanpah is small enough that when I'm in the middle of the playa, most of the band 4 light is coming from off of the playa. So it's coming from about, let's say 1 kilometer away. This is darker than the Ivanpah playa, so I do not get as much band 4 light into band 9. Big playa, I'm getting lots of band 4 light now because the reflectance is very high in band 4. Not so much, lots. And that matches. And then White Sands is even bigger than Railroad Valley, plus the reflectance difference, plus the water vapor effect, plus everything else, and it's just a pathological situation, ends up way up there. So here is a site-dependent problem. And the fact that we had a sensor that we trusted that was showing good results, we had sensitivity analyses that showed that we should not have an adjacency effect, we should not have a size of source effect, and the fact that we then go to another system with the same sites, and it really should have helped that we were on the same day. So when we were collecting these data for Landsat, it was a half an hour later for Aster. And yet we still could not convince people with the very first data set that there was a problem. It was, you have a water vapor absorption issue in your vicarious calibration. And you don't have that in Landsat, so that's why it looks okay in Landsat. Landsat band 8, you guys aren't worried about that? And so it's trying to get to where we develop an error budget that people will actually believe. We're still not there in reflectance-based methodology. We'll get there eventually. But it is something that it helps. And in terms of another ETM Plus master sampling strategy, it just shows, again, the shortwave infrared differences out here in terms of what was happening between them and the fact that we can do comparisons. I won't even talk about the band 1, 2 of Aster, or 2 and 3. This one they had finally changed some of the effects with band 1, but we still had some issues with band 2 and 3. It was always a fight to try and get the different groups within the Aster science team to agree on, we really need to change the calibration coefficients. And again, it was, well, you have these large uncertainties because of repeatability and things like that, and so we'll wait for another data set. Let's wait for another data set.